A very good day to panel judges and everyone. Thank you for coming today. I am Sri Govinda Naidu and I am looking forward to talking with you today about PLA hybrid biocomposite. The title of our project is The Utilization of Nypa Frutican on Enhancing Mechanical Properties of Polylactic Acid. Let me introduce our supervisors and team members. I are Dr. Muhammad Shami bin Muhammad Rasidi, PM Dr. Firuz binti Zainuddin, Muhammad Nur Hakim bin Termizi, Sri Govinda Naidu, Ananaki T. Velu. Since the 1950s, around 8.3 billion tons of plastic have been produced in the worldwide. 73% of beach litter worldwide is plastic. 90% of plastic polluting our oceans is carried by just 10 rivers. Plastic is killing more than 1.1 million seabirds and animals every year. Plastics accounts for around 40% of the global market for consumer packaging such as food and non-food, and plastic packaging is growing faster than any other materials. The limitation of petroleum-based polymers an environmental issue has promoted the potential of polymer from renewable resources in the future market. PLA are stiff and brittle materials, and it is therefore necessary to create composite with other materials such as natural fiber. Nypa Frutican are an agricultural waste is a potential filler in biocomposite. The utilization of Nypa Frutican not much reported in the research study. This project is to replace the polyethylene films that cause environmental problem and issue with the PLA cellulose NFS biocomposite product that can help in decreasing the usage of petroleum waste materials. Tensile testing and surface morphology characterization was carried out. All these tests need to be carried out to determine each of properties for this product to fulfill demand of market needs. PLA hybrid biocomposite is specifically designed to replace the polyethylene films as a food packaging. PLA is fully biodegradable plastic and made from combination of jackfruit seed, starch and oil palm based plasticizer. The PLA product can be processed on a traditional melt blending or by using extruder for industrial applications. The applications of PLA cellulose NFS biocomposite are such as packaging and 3D printing. The methodology part involves material, formulation and procedure.
This is the raw material for PLA cellulose Nypa Frutican shell hybrid biocomposite. Our first raw material is polylactic acid PLA, which is in pellet form. Our second raw material is pure cellulose as our filler.
Materials that are used in this project is polylactic acid, chloroform, pure cellulose and Nypa fruticans. PLA cellulose NFS biocomposite is prepared by solvent casting method. PLA pellet was dissolved in chloroform in a beaker by using a water bath at 60 degrees Celsius using a mechanical stirrer for 30 minutes until it is fully dissolved and a clear solution is achieved. Cellulose was added and stirred for 10 minutes, then the NFS was added into the PLA solution at different formulation ratio as shown in table 1 below and continued stirring for 10 minutes before being casted on the glass plate. The casted PLA cellulose film was dried in closed environment for 48 hours before the sample is ready to be tested. As can be seen from table 1, these are the formulation ratios of PLA cellulose NFS biocomposite film. For the testing and the characterization of the biocomposite, there are two testing has been carried out. One is tensile properties and another one is scanning electron microscopy. For the testing and the characterization of the biocomposite, there are two testing has been carried out. One is tensile properties and another one is scanning electron microscopy.
Tensile strength of PLA cellulose NFS biocomposite. The figure shows the effect of NFS content on the tensile strength of PLA cellulose NFS biocomposite. The addition of NFS into the PLA cellulose biocomposite has increased the biocomposite strength from 1 php of cellulose until it peaked at 65 php, then it starts to decrease at 40 php of NFS content. Elongation at break of PLA cellulose NFS biocomposite. The figure shows the effect of NFS content on the elongation at break of PLA cellulose NFS biocomposite. The trend shows that 5 php of NFS has the highest value of elongation at break, and as the NFS loading is increasing, the elongation at break decreases until 35 php of cellulose. However, the elongation at break trend shows slight increment at 40 php of cellulose, and it is noted that the elongation at break of PLA cellulose NFS biocomposite is lower than the elongation at break of pure PLA. Young modulus of PLA cellulose NFS biocomposite. The figure shows the effect of NFS content on the young modulus of PLA cellulose NFS biocomposite. The young modulus value is gradually increasing from 5 php until it peaks at 40 php of NFS content. The value of young modulus of PLA cellulose NFS biocomposite is higher than the pure PLA young modulus. For the morphology analysis, pure PLA has smooth surface than the PLA cellulose NFS biocomposite, which has rough surface with the occurrence of fiber pull-out. We can conclude that as the NFS content increase, the tensile strength of the biocomposite will increase, the elongation at break will decrease, and the young modulus will increase. And from the morphology analysis, we can conclude that pure PLA has shown smooth surface, and as the NFS is incorporated into the biocomposite, rough surface is observed as the fiber pull-out is occurred.